Welcome back everyone. In this lecture we will define the G action on tensor products, symmetric products and alternating products. So, let us first define how to define this G action on the tensor products. So, we start with let us say K vector spaces. So, let us assume that they are also G representations. So, let us say K G representations are given. So, if you want for simplicity you can just assume that they are all finite dimensional. So, they are finite dimensional and let us say they are given by this maps rho I, which is a map from G to GL Vi. So, now what we want to do? We want to define this G action on the tensor product. So, let us see how one can define. So, let us write it as rho I tensor I range from 1 to k. So, this is a map from G to GL of V1 tensor etc. Vk. So, now define this map as follows. So, it is a natural action on the individual simple tensors that we can expect. So, you take G and then you send it to the tensor product of this rho I G. So, we have this rho 1 G acting on V1 and so on, then rho k G acting on Vk. So, now we can actually consider this tensor product of these maps. So, that is the map actually I am going to just send it to. You look at this tensor product of this rho 1 G etc. rho k G. So, that is the image of G under this tensor product map. So, this actually makes this V1 tensor etc. Vk as a representation. So, that is something one can check directly. So, I am going to leave it to you. So, if you use some simpler notation, so then the same thing can be written as follows. So, we want to define the G action on the tensor product. So, maybe we can take how it is defined on the simple tensors. So, if we take this simple tensors V1 tensor etc. Vk and then the action of G on this is just defined to be, it is going to act on the individual components and then take the respective tensors. So, you take rho 1 G and then act it on V1 and then tensor it etc. tensor rho k G, act it on this Vk. So, this is how the action on the tensor product is defined, where V1 etc. Vk. So, they come from the respective individual vector spaces. So, if you want to oversimplify, if you do not want to write down rho I and all and then assuming that there is this action on this V1 etc. Vk. So, we can use much more simple notation. So, we can just write this as without any rho i's, just you write simply as GV1 tensor etc. tensor GVK. And it is easy to verify, this is going to give you action on the tensor product. And this is what we call as tensor product of representations. So, now similarly you can also define G action on the tensor algebra. Okay. So, to begin with the tensor algebra is a C vector space. So, this is indeed graded space. So, the kth graded piece will be just TKV, where k range from 0 to infinity. But what is TKV? TKV is nothing but k fold tensor of this V. Since V is G representation, if we start with let us say V is G representation. So, then it is easy to see that this TKV becomes G representation. So, in particularly TV also becomes G representation. Now, note that TV is indeed infinite dimensional G representation, but it is graded representation. one can talk about graded character of that. So, we will actually come to that later. So, now we are going to define this the same G action on the symmetric algebra and as well as on the exterior algebra. So, for that we need to actually check that the ideal that we are actually going modulo is indeed G invariant. So, recall that S of V is given by T of V modulo this ideal I, where I is two sided ideal generated by this x tensor y minus y tensor x for all x y in V. So, now if you want the action of G on S of V, so we need to verify that this I is indeed G invariant. So, verify I is indeed G invariant. So, once we have this fact I is G invariant, then the quotient will inherit natural G action. So, that will make S of V as G representation. So, why is I is G invariant? So, one can easily check that it is enough to verify G invariance for the generators. So, the generators are nothing but x tensor y minus y tensor x. So, if you apply G on this x tensor y minus y tensor x, so you get exactly equal to gx tensor gy minus gy tensor gx, which is going to be element of I. Okay. And since this is true for all x y in capital V, so indeed this is what gives you that I is also G invariant. So, maybe I will leave it to check. Okay, this is the exercise. The exercise is check that it is enough to prove the following. And which is easy to verify. So, that makes this S of V into G invariant space, sorry, G representation. So, this I into G invariant space. So, S of V is indeed G representation. So, this also becomes G representation. So, now note that we have this decomposition of S of V into direct sum of Sk of V. So, we can ask whether this Sk of V is also indeed G invariant or not. Okay. And one can easily check that is indeed the case, because SKV you can identify as the image of TKV. So, the map that you have from TV to TV modulo I, so that is indeed G map. Okay. So, this map pi from TV to SV, which is TV modulo I, is indeed G homomorphism. So, that makes all the images SKV, because this is just image of TKV. So, these all becomes G invariant subspaces. Okay. So, then indeed this S of V breaking into this Sk of V is indeed G invariant decomposition. Okay. So, again, since this is infinite dimensional and it is graded, each graded space is G representation, one can talk about what is called graded character for this. Okay. I will talk about the graded character in a minute. So, maybe let me define what is the graded character. So, the graded character of an infinite dimensional representation is defined as follows. So, we take this graded infinite dimensional representation, let us call it V. So, this is graded. So, let us say grading is given on this G plus. So, this V you write it as direct sum of Vk, where k ranging from 0 to infinity. So, let us say this is indeed G representation, such that each Gk each Vk is also a G representation. Okay. So, now what is the graded character of V, of course applied on G in G. So, this is defined to be the formal sum, the individual character of Vk applied on G, and then you keep track of that using this t power k, where k ranges from 0 to infinity. So, this is the generating series of these characters of this Vk, where the tk power coefficient is given by the character of Vk. Okay. So, this is what we call it as graded character, and we will compute graded character for this tensor algebra, symmetric algebra, as well as the exterior algebra. So, this is indeed graded G representation. So, this is indeed graded G representation, and similarly T of V is also graded G representation. So, now let us look at this symmetric products that we have defined before. So, recall that the symmetric product, which is indeed subspace of this TKV. So, the way we defined, one can take it to be the image of the symmetrization, or one can also look at this action of Sk and then realize this as the fixed vectors. So, let us recall, this is those x in TKV such that when you apply sigma on this x, we are going to get x for all sigma in Sk. So, this is what our symmetric products. Now, since the action of Sk on this TKV that actually commute with the action of G on TKV, so that actually makes this symmetric K of V to be G invariant. Okay. So, it is an easy exercise that one can prove that the action of this symmetric group Sk on this TKV, that is indeed commutes with your G action. So, let me spell it out for G in G and sigma in Sk. So, we have the following. So, you apply first sigma on the simple tensors V1 etc. Vk, and then apply G on that is going to be same as applying sigma, first is G and then sigma on this V1 tensor etc. tensor Vk for all V1 etc. Vk from this capital V. Okay, this is the meaning of the action of G commutes with the action of Sk on TKV. Since these two actions actually commutes, then it is easy to see that this fixed point subspace under the action of Sk, that is going to be G invariant. So, as a corollary, one can easily see that sim Kv is indeed G invariant. So, this actually tells you that why this is indeed subrepresentation. So, now we already have this isomorphism between SKV and SymKV, and it is again easy exercise to prove that these two are indeed isomorphic as G representations. Okay, that is not very difficult to prove. Okay, so what's about the alternating product? Similar story happens even for the alternating product. Let me just state it as exercise. Again, since the action of Sk commutes with the action of G, the alternating product, so that is also going to be G invariant. So, this alt K of V, recall this is by definition you collect those vectors in the K fold vectors such that which is indeed gives you this following: sigma x is going to give us sine of sigma x for all sigma in Sk. And since Sk action and G action commutes, so this is also a G invariant subspace that will follow easily. So, let me maybe check it for you. So, if you start with x in alt kv and apply gx, then if you take sigma gx, it is going to be g sigma x, and now you can see that sigma x is going to give you sine. So, this is g sine sigma x, and g is linear. So, the sine will come out and then you get gx. So, this actually simple verification tells you that alt kv is indeed G invariant. And similarly, one can check that the exterior algebra, so that is also G representation, and the exterior products lambda kv, they are also G representations, and this is graded G representation, and these are all the graded pieces. So, now it is not difficult to see that lambda kv is isomorphic to this alt kv as G representations for all k greater than or equal to 0. Okay. So, this is something very easy to check. So, we also had this factorization of this V tensor 2 as sim space and alternating space, and that factorization is also going to be factorization as G representation. So, if we take V tensor 2, so this is naturally isomorphic to this sim 2V direct sum alt 2V, and this we have seen as vector spaces. But now, if we start with V being representation, then this is also factorization decomposition of this V tensor 2 as representations. So, G representation we have this. Now, what is about the characters? So, the characters of the tensor products is easy to compute. So, let us say as before we have this V1 etc. Vk, these are all the G representations, and we can put it to be finite dimensional G representations. So, now if you are interested in computing the character, so recall that the character of this let us say rho 1 tensor etc. rho k of G. So, what is this is going to be? This is going to be the trace of this rho 1 G tensor etc. tensor rho k G. So, now we know how the trace behaves with respect to the tensor maps. So, the trace of the tensor is just the product of the traces. So, this is going to be exactly the product the traces of individual rho I of G for I range from 1 to k, where rho I is the representation of this Vi, okay, for I range from 1 to k. Now, from this you can conclude that the character of the tensor is nothing but the product of the character. So, this is what already expected. So, the direct sum is indeed giving you the sum of the characters, and the tensor product is giving you the product of the characters. So, basically the character map is well behaved. Okay. So, if you are looking at this representation space, okay, the representations of G, which are the finite dimensional representations of G, and then if you take this what is called this character ring. So, the character ring, so where you consider all possible characters of the group G coming from the representations. So, then the direct sum map to the sum of the characters, and tensor product map to the product of the characters. Okay. So, basically the characters are well behaved with respect to the direct sum and tensor products. Okay. So, what is about the character of the the symmetric product and the alternating product. So, let us do one example and then I will actually do the general construction and proof. So, as an example, let us look at two-fold tensor product. Okay. So, here is the proportion. So, let us take V being 5-dimensional representation of G. So, what we are interested in? We are interested in computing the character of sim to V and then character of the alt to V. So, let us try to compute what it is. So, recall that we already have this decomposition. So, V tensor 2 is exactly sim to V direct sum this alt to V. So, that means the character of this V tensor to V of G is going to be exactly the character of sim to V of G plus the character of alt to Vg. So, this is already there. So, this means it is actually indeed enough to compute one of them, because we already know what will be the character of the tensor. The character of the tensor is just the square of the character. Okay. So, let us compute what is the character of the sim. So, for that what we are going to do? So, we are going to fix an element G in G and then compute the trace. So, let us fix G in G, and we know that rho of G is going to be diagnosable operator acting on V. So, let us say rho is the representation from G to GLV, then rho of G is a map from V to V, and since G is finite, so there exists. So, if we call this capital N to be the cardinality of G, then rho G power capital N is going to be rho G power N, which is exactly the identity. So, that means rho G is diagnosable and all the eigenvalues of rho G are nth roots of unity. So, rho G is diagnosable. So, what we are going to do? We are going to fix a eigen basis of V for this rho G. So, let us list it as V1 etc. Vn. Okay, this is the, let us say, eigen basis. So, this is indeed eigen basis of this rho G acting on capital V. Okay. So, basically this basis of V. So, with the respective eigenvalues, we denote it by lambda 1 etc. lambda n. So, these are the eigenvalues corresponding to the eigenvectors V 1 etc. V n, and it is of course counted with multiplicity. Counted with multiplicity. So, now what we can see that so once we have the basis V 1 etc. V n, if this is the basis of your capital V, then we already know that what will be the basis of the alternating product as well as the symmetric product. So, let us write down the basis of the alternating product. So, you take this V I tensor V j and then minus V j tensor V I, and this is going to be actually basis of the alternating product. So, you take all possible this difference with I less than j, where I n j comes from 1 to n, and this is indeed a basis of this alt to V. Okay, that is easy to check, and it is not just a basis, it is indeed eigen basis. So, what will be the eigen values? So, we are talking about the induced induced operator on this alt to V. So, rho G is acting on V. So, rho G will act on V tensor V. So, in particularly, so rho G is going to act on this alternate alt 2 of V. Okay. So, this is there from V tensor 2 to V tensor 2, and then you can take this and then restrict to alt 2v. Okay. So, this is the operator that we are talking about, and this is going to be eigenbasis for this operator. And what will be the respective eigenvalues? So, with the eigenvalues it is easy to see. So, the eigenvalues of Vi tensor Vj is going to be lambda I times lambda j, and since this is just a difference of these two eigenvectors. So, the same eigenvalues you get with the eigenvalue lambda I times lambda j for I less than j. So, this will be the eigenvalue. So, that means the character alt 2v of g is going to be the sum of the eigenvalues. You sum it over lambda I lambda j, where I j runs over from 1 to n such that I less than j. Now, this can be rewritten as follows. So, if you think about it, this is just of times you take all possible sums and then square it, and then take minus sum of lambda I square, where I range from 1 to n. Okay. And this difference is going to be exactly this. And what is this? This is exactly the chi v g. So, this is exactly the chi v g square. So, if you just substitute there, so this is exactly chi v g and this is exactly chi v g square. So, if you substitute there, so what you get? You get chi alt 2 of v of g is exactly of times chi v square g minus chi v of g square. So, this is what we are getting. So, now if we use this, then we will be able to compute chi of sim 2 v. So, what is chi of sim 2 v? So, recall, so this is going to be coming from this following identity. So, this chi v g square minus this chi alt 2 v of g is exactly equal to chi sim 2 v. So, that means what we have here is chi v square g minus of chi v square g minus chi v g square. Okay. So, this is going to be exactly equal to of chi v square g v plus of chi v g square. So, one can take the of outside. So, if you take it outside, then you get exactly this. So, this is going to be the character of the sim v g. Okay. So, this actually tells you that the character of the sim 2 v and the character of the alt 2 v can be obtained using basically the characters of g and characters of g square and so on. Okay. So, only character of g and character of g square will be used here, and similar thing can be done even for the higher order symmetric product and alternating products. So, maybe I will do that in the next class. Thank you.